Welcome again from me. I missed the beginning. I'll explain why. So, the topic of today, serverless at Studyportals. Who of you has heard the word serverless? Just to get an idea. Okay, who has worked with cloud services before? Cool. Okay. So, my name is Daniel. I'm a backend engineer. And I'm still a student. I'm doing my bachelor degree now in software engineering and a minor in computer science. So yeah, I forgot I have the mic. And I'm 22, and this is my first talk in front of complete strangers. So yeah. Okay, a little bit about myself. I really like going to parties. I really like hiking in the mountains, and this is the main reason I moved to the Netherlands. Yeah. So, I don't know how much Danko told you about our company. So we're an international study choice platform, and we help the students through their journey of exploring, comparing, deciding and applying for their dream study abroad. Some statistics, we have a lot of studies, like more than 240,000 of them, which are spread across 128 countries. So that's quite a big choice you have for where to go. And the user base we have comes from 236 countries. I'm saying all those numbers to make you understand that we're dealing with a big number of people and that our services need to adapt to those numbers. So 3.5 million users per month, 17 million page views, and around 4,500 new registered people every single day. Engineering at Studyportals, I think, is quite usual. In other companies, probably is the same. So we work with Scrum. We have 8 independent Scrum teams, plus the big data team and DevOps, which are more like umbrella on all the other teams. And my team is called X-Minions. So every team has this cool name, like Ultimate Avengers and X-Minions and League of Extraordinary Gentlemen. Awesome, right? So in our company, we have this concept of a user journey funnel. So this is a way that we can categorize people and where they are in their journey of finding their dream study abroad. And each team is responsible for part of that funnel. So it's a bit easier to take the user and guide them through your part as quickly as possible. And then we want to increase the number of people that goes through the funnel. So then in the end, more people can end up applying for their dream study. So I'm going to tell you about the story of how we built the new student system. So why is it new? Of course, there's something old before it. Back in March 2017, this was the situation. So we had 2.5 million people already in our databases, and we had this one big monolithic service that was doing everything. So it was doing everything related to users, everything related to studies, analytics, everything in one place. It was written in PHP, and the code base was, I think, almost 10 years old, which is quite a lot. So you can imagine there was a lot of spaghetti code, things built on top of each other. So it was really hard to extend that system and make it fit the new requirements that are emerging from us just exploring what more can we do to bring users through the funnel. So the number of people who were registering was growing, and the query of data, so people wanted to get, for example, their favorite studies, they say. And those queries were becoming slower and more difficult because we had a lot of tables in our relational data model. So every time you want to get something, you need to join all those tables. And with the growth of users, you have to join even more and more rows. So the queries started to become slower and slower, and the users were starting to see that. So scalability became an issue. Around that time, we also had some movements in our team. So some people left, some people were moved. So it was quite unstable. We also didn't have a clear goal of what our team was supposed to do. So a bit of a rough time. And this is why it took us 4 months to make the team stable again and we can accept the challenge of building something new that could handle tens of times more users than what we have back then. So we made an awesome service checklist. So all the issues we had before, we had to address in some way. So we wanted to be independent from everything else. So we decided to go with the microservice architecture. So we can remove only the student part of the old monolith and move it to its own thing. So it can scale independently, it can be developed independently, we can choose our own language, our own technologies, and as I said before, make our team completely independent from everyone else. Another thing, scalable, of course, the main reason why we're doing it. We wanted to get more people in to store the information and to give them more value. So back then we started exploring the option of making a serverless service, basically. I'm going to talk a lot about that, how the journey went through, because it wasn't just, yeah, let's do it, it's super easy like all the materials say. So this is why I think you see something useful, because usually all the marketing around serverless those days is, yeah, it's easy to start, it's super fast to get it going, but if you want to do something in production that is going to be used by so many people, you can't just hack something together and expect it to work forever and build upon it, because then we would end up in the same place we were before, where we just build something so it works, and then at some point it starts becoming ugly and you have to redo it again. So, of course, speed was an issue, so our service had to be fast. We did that through a lot of optimizations on the serverless stack I'm going to introduce in a bit. Reliable, of course. We don't want people to get errors or some bad data or some bad advice. So we try to introduce the concept of automated testing in our continuous delivery pipelines, which we also build with Amazon, to ensure that everything is doing what it's supposed to do, because the old monolithic service didn't have any tests whatsoever, so it was basically faith. I hope it's working. So we also wanted it to be fully cloud native. Before we started moving to Amazon, I think we had some machines in a data center somewhere in the Netherlands. They were going out sometimes, so relying on Amazon would mean more consistent performance and availability. And last but not least, we denormalized the data model we had before to make it even faster to retrieve data for the specific user at the moment. And for our implementation, we chose a document store, and Amazon has that in the eyes of DynamoDB. So, our architecture, I'm using a lot of pictures, a lot of Amazon Web Services names. I don't expect you to know what they are, but I am going to talk what they do. So, first of all, we have a web platform. We have a website. So people go to a web page and they see something. We also have the concept of microservices on the front end, where what you see is not actually coming from one server, but it's being assembled from different small services together and then shown on the page. So then each team, again, can be independent from anyone else. And then if something else breaks, you're still protected and you know that your product works. So to do that, we have our serverless front-end stack, which is CDN and a data storage. I am going to talk about it in a bit. Then, of course, we have our serverless backend. And then we have another part that I call the event-based data replication. So because now we switch to a document store, all the aggregation queries that our big data team were doing before were no longer possible, because you can't just select all from the table and then do some aggregations on it. But we still needed to support that business capability because other people were relying on it. So we needed to find a way to replicate the data from our main document store to all the other services or people who need it. So we built this part. Of course, I mentioned continuous delivery. we also have a serverless implementation with Amazon for that. And an important part of any big software project is monitoring, so performance. And I'm also going to mention which of the Amazon services we're using. So everything you see here is serverless. So there is not a single thing we need to manage specifically or to be worried that it might go out or we might lose a node. Everything is managed by Amazon, so we can just work on what matters to our users to implement new features and not to worry about what is going on with our servers. Cool. So the first part, the static front end. So we have 7 front-end microservices which are being loaded on the page every time you visit it. And this happens through a service called CloudFront. This is basically a optimized CDN which has multiple locations around the world to ensure that you can get the thing you want as quick as possible. And the data, so the static files, HTML and JavaScript and CSS, are stored in S3, which stands for Simple Storage Service, which has the option for website hosting. So with those 2 components, we can just put our files in the S3 bucket, and then we have a global optimized CDN that can serve millions of requests per month, and we only pay for storage costs, which is a few kilobytes at the worst case, so it's basically free. And then we have the CloudFront distribution that ensures we have proper caching, so we don't serve the same thing multiple times for free, basically. Of course, there are some costs on requests, but that's not so much. I'm going to make a bill in the end. Our scalable API. So this is how our infrastructure looks like. It's a visualization of the different parts of it. So basically we have 5 APIs which are built on the serverless stack. So we have API gateway, which basically we use to handle all the requests that come in and forward them to the correct handler, so to run the correct code. And that code is executed on Lambda, which is basically the biggest serverless part in Amazon, which allows you to just run a snippet of code in response to an event. And in this case, the event is a request, a network request that is coming to API Gateway. For authentication and authorization, we're using AWS Cognito on the bottom, which is basically a user pool where users can register with their username and password. So we move the responsibility from us on the security side to Amazon, and they keep all the best practices for handling the passwords and refreshing and so on. So we rely on Cognito to make sure that every user has their credentials stored in a secure way. And as I mentioned before, our data store is DynamoDB, which is a document store where we basically keep the normalized record of each student. So when they want to retrieve their data, we can just query it from the table and give it back. So we have multiple Lambda functions in those APIs. Basically, every path that you can send, every request that you can send is being handled by a separate Lambda function. So we have 12 endpoints. That would mean we have 12 Lambda functions, each handling one part of the whole API. So imagine if you deploy a similar API on a server. That means that your whole code is in one place, and then if you have an error in one of your endpoints, the whole thing goes down. In this case, if we have a problem in one of the endpoints, only this endpoint will go down, because everything is separated, and yeah, that gives us the extra flexibility. Plus, we don't have to worry about managing servers, which is quite cool. Now, the cool part, the event-based data replication. It sounds really nice. So we have basically two requirements that need to fulfill here. We have a few emailing marketing systems that our community and intelligence team uses to send marketing emails. and they require a subset of the data of the users to be present in their system. So they can create dynamic emails with some nice and interesting content. So we needed to make sure that we are replicating the data from our main store to the emailing marketing system in real time. And the other requirement was to connect our data warehouse, which the big data team is managing. We're using AWS Redshift for that, so they can do all the analytics and aggregation queries on top of the whole set of users we have. And everything needs to be as real time as possible, so that the queries they're doing or the emails that are being sent are up to date with what is in the main store. Of course, it's eventually consistent because it takes some time to replicate, but we try to reduce that time as much as possible. So what are the different components we're using in this case? So on the top, does this thing work? No, it doesn't. Okay, so on the top left, you see our document store, DynamoDB. There is a feature called DynamoDB Streams, which basically is like a tail log in the normal relational database engines, where you have all the updates that are happening to the items in your database emitted as events. So every time someone inserts, updates, or deletes something, we get an event in that stream that says this is the old value, this is the new value. So we have a delta of what changed. That can be connected to Lambda because, like I said, Lambda is event-based. So a DynamoDB stream change is one of those events. So you can subscribe to that, and from then on, because we have to replicate the data in more than one place, we need to have a mechanism that we can broadcast that this event happened. For that, we're using AWS SNS, which is Simple Notification Service, which is basically like a pub-sub mechanism where you can send messages once, and then you can have multiple subscribers that receive that message. As subscribers, we have mainly two options. One of them, of course, is Lambda. So then we can, then we can split the data. Or, for example, in one of the emailing systems, Copernica, we know that their API is quite slow. So if we push that data in real time, it might throttle, and then we start having the request fail. That's why we have a buffer in front of Copernica to store all the things that it needs to save until the service is available. So a nice use case for that is AWS SQS, which is a simple queuing service. So you see, like, all those small serverless components that by themselves, they're not really special, but they start working together in one big system to achieve that real-time data replication. And the last thing is on the bottom right. I don't know if you can read it. It's called AWS Kinesis Firehose. So Kinesis is a streaming service, which is basically, I don't know if you heard about Kafka. It's comparable. Basically, you can send information to that stream, and then Amazon handles all the provisioning of the resources, all the synchronizations, all the ordering within the messages you're sending. And Firehose is really special because it is automatically scalable. So we can push as much data as we want, and we can be sure that Firehose will scale automatically. And then you're built for the amount of data you're sending. So if we want to send a little bit, we send a little bit, it works, we pay a little bit. If we want to send a big amount of data, we know that the system will handle it and it won't become a bottleneck. So all of that stuff coming from the database with the streams reflecting all the changes from Lambda, sending a notification to all the subscribers who are interested in that, and the queues and the streams provide us with a resilient solution to make sure that we have all the changes that happen in the main data store reliably copied to the auxiliary data stores. Is it clear? By the way, if anything is not clear, just stop me or ask questions meanwhile. Cool. last part. We have reliable monitoring and continuous integration and delivery. So, of course, when you have a service, you want to make sure it's running correct. Even though it's serverless, that doesn't save you for your own bugs. So if you have introduced a new bug in the system that is distributed across, let's say, 20 Lambda functions, you need to know where the problem is so you can fix it fast. So using a combination of services to achieve that, again in real time. One of them is CloudWatch, which is quite extensive. So usually you have a logging server where you send all the logs from your machines to, then you can aggregate them. In the serverless world, there is no servers, so where do you send your logs? Basically, Lambda handles that by sending everything from your execution to a central place which they call CloudWatch. And from there you can do, again, the replication, you can do alarming, and you can do a lot more. And on top, all the small circles you see, this is a service map from AWS X-Ray. Basically, what this allows us to do is have a visual representation of all the small pieces in our serverless architecture and their performance in real time. For example, one of those circles can be a Lambda function, saying, okay, it takes so much time to execute it, and so many of the invocations are successful, and we have so many errors. Or it can be a DynamoDB database, where we can see the provision capacity for the table is exceeding the one you mentioned, so we have some throttle requests. Of course, we have our database turned for auto-scaling, so if we have more load, it will just scale automatically. We don't have to worry about that. It's serverless, so we're not worried about losing data because we also have automated backups, and we only pay for what we use. So I think I'll mention the bill later, not to ruin the surprise. And then another thing we have is Amazon AWS Elasticsearch, which is basically a managed Elasticsearch without servers again. And we have AWS Athena, which is quite special. We're not using it that much, but imagine you have a stream of information, for example, some events. And then with Firehose, you can stream those events to an S3 bucket, which is the object storage. So then in the end, you have many files that contain those events. So you can save them for later or just some backup so you don't lose data. What Athena allows you to do is run SQL-like queries on the data sitting in S3. So you get basically a database where you can put unstructured data, and you can use Athena to search through the contents of the files that are in S3. And everything you pay for is the amount of files you scan. So that's quite awesome. We're not using it that much, but I just wanted to throw it out there in case someone wants to try it. It is really cool. Please do try it. Yeah, I'm sorry, sometimes I get a bit enthusiastic because like the first time I saw an Athena query run, and I'm like, what? You can just scan over the contents of the files in real time? And this scales really nicely. We had some examples from Amazon, of course. They were going through 2 petabytes of data. That's insane amount of information. But back to the point. So we have our, we also have our continuous delivery pipeline, which is again serverless. So this is comprised by 2 Amazon services. So we have AWS Code Pipeline and AWS Code Build. The code pipeline, it's a bit like Jenkins, where you can just create different stages of the pipeline, which you can do different things on. Of course, it's also integrated with Lambda, so you can use that to notify something or trigger something else. And then for the actual building part, you need to run some scripts probably. So this is where AWS Code Build comes in. Basically, you can put a single file in the repository you're trying to deploy, which contains all the commands that need to be executed in the appropriate build step in your pipeline. So then, for less than 10 minutes, you can create a continuous delivery pipeline where you have the GitHub as a source. So every time you push to a specific branch, the whole pipeline starts, the code is copied, then the build step is done, and then usually you deploy it to a server, because this also works with servers. But in our case, we're using a framework which does the deployment for us, so it's basically running one command. This is also where we run our test suite. So we have unit tests, we have end-to-end tests, and for the main API, the student API, we have a setup where when we open a pull request, we create a completely new environment. So all the small pieces you saw, they are described as code in CloudFormation, which basically allows you to describe every part of your infrastructure as code. So you can also version that. And then it creates a completely new testing environment where we can independently test all the functionality that we expect to work. And then if that works, then we deploy. If it doesn't, we fail and we send a notification. So there was a lot of planning and a lot of new words. And of course, as you can see, it took us quite some time to figure out what are we dealing with, how would those small components talk to each other, and how do we achieve the goal that we had in the beginning. So in October 2017, we started cooking. So we started building, and of course immediately we hit some roadblocks. One of the main things in the beginning, because our company was also quite young in the transitioning to the cloud, so we didn't have much experience with that, and we had a problem of not fully understanding what each service does and what its constraints are. So I imagine some of you are hearing a lot of those names for the first time, and you're like, oh yeah, that's cool, but when you actually start working with it, there are a lot of small details that you need to get right. And those details are really hard to find in the documentation, because of course Amazon, they have a lot of services and everyone is described in the best way I hope they can. But again, finding the information you need for the problem you need is quite hard. And especially if you don't have anyone else to ask around you, because everyone is new, so you're still learning, it's also quite hard. Another important thing, which I think is quite important for the topic of today, serverless at Studyportals, is some serverless quirks. So on marketing paper, it might seem really fast and easy, but there are some small details, like I mentioned before, that got us in the beginning, because we didn't really know what we were doing. For example, we have cold starts, because we assume, it's not officially documented, that the Lambda code that you're submitting runs in a container. So to do the optimization, we assume that Amazon reuses containers. And we have no idea how many times one container will be reused. So imagine your API is not having any requests whatsoever. Then one comes in, and then the Amazon infrastructure needs to create an environment for your code to run, which in most times takes a long time, up to 10 times more than what it normally would. Of course, it happens once, and then you have a hot container that can be reused for several invocations. But if you have a burst of requests, for example, if you send 200 requests at the same time, you will get 200 cold starts, because each request needs to be handled by a separate handler, and you don't have any at the moment. You need to spin up 200. So that's one thing to keep in mind. Another thing is cached variables. So in the code you submit to Lambda, there is a part, it's called a Lambda handler, which is basically the part that gets executed. But in your code, you can load modules and initialize variables before that handler. What we didn't know in the beginning is that because the containers are reused, those variables are also cached. So Lambda guarantees that only what's inside the handler will be fresh. So in the beginning we had some side effects where we had some control objects that were handling each request that had state in them. So if you initialize them outside of this handler, then the state might be affected by the next invocation, and then you have really interesting side effects that at first we didn't know what was going on. Because you send one request, it goes well, then you send another request immediately after that, and then it breaks. And then they're like, what's going on? So it took us some time to find that out. Another thing was API latency. So when we deployed our first serverless API, and we started testing it, and it was disappointing. It was really slow. It was like 500 milliseconds per request. That's unacceptable. So we were wondering why that is happening. Our code is not doing that much. It turns out that in Lambda, you can set the memory allocation that your function will use. So how much RAM does it need? And that varies from 128 megabytes to 3 gigabytes. And apparently, the amount of memory you choose can also be correlated with the speed of the code execution. Again, we assume that this is running in a container on a machine. So if you say you want more RAM, then probably you'll end up on a bigger machine that is also faster. So then your function becomes faster. And then we decided to bump up the memory all the way up, and then it was really fast, like sub 50 milliseconds, which is awesome. So there is a sweet spot where if you keep increasing the memory, you don't get much more speed. And that's of course trial and error depending on what you're...
more CPU.
Sorry?
You get more CPU.
Yeah,
It's
indeed.
The same if you use 4K, it's the same size also.
Yeah, so it really depends. You need to find that spot where even if you increase more, you don't get that much performance. For example, if you go from 128 megabytes to half a gigabyte, then you get, for example, a 6-fold increase. But if you go double that, you only get 10 or 15 more %. So you have to experiment with how much memory you allocate in order to reach your speed requirements. And last thing is deployment. So now you have, let's say 12 endpoints, you have 12 functions, and each of them has its own dependencies, and it needs to be deployed to Amazon. So how are we going to do this? The original way is you can use the integrated IDE, but for our project, which is quite big, there was not really an option. So we started looking at tools that can help us, and the tool we picked is the Serverless framework, which basically allows you to define your API in a file, and then it handles all the packaging and all the deployment for you, so you don't have to worry about that. So this is how we solved deployment. Another thing we had to keep in mind is transitioning. So we have this old monolithic service running in production. We have people who are using it every single day, so they keep registering. But at the same time, we're building something completely different. And the requirement was we needed to switch from the old one to the new one without anyone noticing. So no downtime, no lost registration, no lost data. We also had to do that while we're porting the old data store, which was a relational database. So we had to denormalize the data to put it in our data store and keep both of them in sync, which was insanely difficult because we also had a new authentication mechanisms. So everything basically was different. And what we did, imagine if you're in front of the building and you have this one entrance that you usually go through. There is a specific mechanism for authenticating yourself. What we did is we decided to put another door right next to it. So then in the end, we can just flip a switch and redirect all the people from the first door to the next one. And of course, all the systems that handle the authorization would initially talk to each other to say, okay, yeah, this guy is really who they say they are. So now we're going to create a new profile in the new system. So then next time when he comes back, he or she, when they come back, the leading one is the new one. So then if you are there, it's like a cache. So if you are there, you go through. If you're not, we check with the old provider. If they say you are who you think you are, then we let you in, we create a new account, we transition the data. So all those things, they had to be planned out, and it was quite difficult. Which leads me to March 15, which is 4 days after my birthday, which was awesome. So this is what happened on. Come on. It's quite cool. It's a video that when you go to the next slide, it starts playing automatically, usually, but oh well. Will it work? Play? No? Okay, well, never mind. It was a cool video of us launching the new student system. We even created a suitcase, you know, where the President of the United States has this cool suitcase that they walk around and they have like keys and you can press switches and then the rockets launch. That's the same thing we did. So we created an actual suitcase with an Arduino inside, with some keypads, with some keys. When we turn that would send a request to API Gateway, which will be handled by a Lambda function to trigger this transition. So then everyone starts going through the second door we built. And of course, we had a video on the screen of a rocket lifting off, which was hosted on the S3 static website. So all serverless. That's basically us immediately after it happened. And you see all the nice dashboards behind because we had to monitor how the transition went. And I'm very proud to say that we didn't have any errors, so everything went smoothly. And the only thing the users noticed is that everything became really, really fast. So, since March until today, we're keeping a close eye on everything. We built some real-time alerts. As I mentioned before, we're using AWS Elasticsearch, where we're sending a lot of tracked events from the front end. So every time you start the registration process or you start logging in, or there is an error when you try to save something, we save those events in Elasticsearch, and we have a dashboard. We had a dashboard which would indicate that there is a problem 1 minute after it happened. But because we're trying to be more KPI oriented, we decided to remove that dashboard and put something that is more user focused and not so much process focused. So in order to keep track of everything that was going on, we decided to build alerts. So basically, on a schedule, we can run a Lambda function, which is another event that is supported by Lambda. Every minute, we have a service that will basically ask Elasticsearch for some metrics. So we have some queries, we get the metrics, and we push those to CloudWatch. So you can use CloudWatch to push custom metrics for whatever is interesting for you. And this enables a really cool feature called AWS CloudWatch Alarms. So based on those metrics, you can configure custom alarms that would be triggered when the certain threshold is passed. So after those alarms are triggered, you can configure it to send a notification to SNS. So you can publish a message that an alarm went on or off. And then, of course, we can subscribe a Lambda to that pub/sub model, and we can push that message through Slack. So every time, every minute, we get the metrics, we push them. If they're above the threshold, we send a message to Slack, and now we have the real-time monitoring that we had on the dashboard, even when we're not here. Now, the bill, please. So, all of that is really nice. You pay for what you use, and how much does it cost? All of that I showed you. So, we have 5 backend APIs with also a little bit more smaller services, for example, the alerting one. And we have 7 front-end services that serve microservices to the front end. Our average latency on the backend side is 65 milliseconds, which I believe is quite reasonable. It's under 100, so it's still good. Can be improved, of course. We're serving 35 million front-end requests through the CDN CloudFront, sorry. We have 33 million backend requests per month. We have 14 million Lambda invocations, so that's quite a lot. Every single component of that big architecture, it's talking to one another, so it's quite a big number. We have 3.5 million messages sent to simple notification service. We have 5 million items queued to simple queuing service. We have 600 gigabytes of data stored in S3, which quite a reasonable amount. It can be more, of course. And we have all the rest. Real-time data replication, analytics, alarming, logging, monitoring, everything that I was talking about, we get in that bill. And the final cost is, can someone guess?
Prices.
Okay, so it costs around $600 to $700 a month, which it might seem like a big number, but this is what you're getting. And I didn't even put the other things because they wouldn't quite fit in the slide. Yeah.
How many DynamoDB requests do you have?
I don't know on top of my head, but we can check after if you want.
Because that is also sometimes quite costly.
True. We have quite a regular load, and most of the times they just reads, which are quite cheaper than writes.
Yeah.
So we're not that write heavy because we don't store that much personal information on students. So our costs mainly come from the automatic backups because they're built per gigabyte. So we have them running, I don't know, every 6 hours or something. So that's the majority of the things. But I think for Dynamo alone, we pay around $60 a month across 5 services. Yes?
And what is then again the functionality that you offer?
Sorry?
And what is then again the functionality that you offer? So the 5 backend APIs and front end?
Yeah,
is
sure.
Is it the whole Studyportal thing or is it?
No, this is only our team.
And what was it again?
So our team, we do registered user experience. That's the marketing word. Basically, we do authentication, authorization, personal data handling, and behavior analysis, and all the emailing stuff, and so on. That's our part. Basically, most of the things that are centered around the students and their information. So $600 to $700 a month. This is equivalent to running 10 large virtual machines. So if you do the math, if you have 5 backend APIs and 7 front-end services, then normally you will need at least 12 machines to handle 40 million requests per month. So yeah, this is the cost. It might look a lot, but we also gained a lot of time, which is quite expensive, engineering time. So because we're not worrying about deployments, about servers going down, about scaling and all of that. So I think the saving in the end, it's quite big. Of course, there are some arguments to be made that serverless can become really expensive, and yes, that is true. And usually the marketed use case is for irregular traffic, event-based systems as well. So there is this point. And indeed, if you create a cluster of smaller machines that can scale automatically, that can also work. But there is, again, some management cost, some consideration to be made that if something goes wrong in your code, the whole service goes down, and all the other arguments after that. So for our future, we came up with some ideas that we can work on. So of course, we want to keep improving the quality of the code base. Because when we started with serverless, you have this new mindset that you need to have, that your project is now divided into really, really small pieces that do one thing. Usually you have one project, you can reuse some things, but we had to comply with Lambda's structure, basically, what you need to submit. and that requires some reorganization of your code, and we were experimenting with different solutions of how we can organize that. So the first code we wrote is quite bad, I admit, but we're learning and we're improving constantly. We're also looking into a graph data store to do recommendations. We have a new dedicated team that does domain-driven design and overall architecture, so we can improve our inter-team and inter-service communication. So again, we're still independent, but we have to work together. So yeah, that's it. Thanks.